Let's see if it will take time. So 19.212 is deriving extension. This should be straightforward, right? Which part are you having problem? Which part do you have? You have problem with all three parts, or which part? The A and B. Okay, so that should be straightforward. But that is just basically just following the same general method. You just F, this is confused, right? Basically, your Fx is x negative. It's a delta function, delta x. And you go back to the general formula. This is the standard form. Period is 2 pi. And then you can go back to the first equation that we wrote down. So that is this general solution is 19.1. Just the standard form, or the cosine term, and x. But this is a period of 2 pi, so En sine x. Right. The standard form is this one, but you need to figure out what the b sub n, a sub n, and b sub n, which you use the standard formula. So a sub n is given n over pi, and in this case, it's integrating from minus pi to pi fx. Right. And fx is such that delta function, so it's a substitute delta function. Okay. And using the property of delta function, you just pick up the function, the value of the function at the zero of the argument of the delta function, which is 0. This is cosine at 0. This is cosine 0 divided by pi, which is 1 over pi. Okay. So all the a sub n's are like that, and b sub n likewise. And put all the sign. And that will give you 0 because at x equals 0, all the sign 0 is 0. All the b sub n is 0. Right? With that, you put it back to here. So basically you cancel all the b sub n, and a sub n becomes 1 over pi. A sub 0 is also 1 over pi. Yeah, that's fine. So when we talk about that as long as it's a periodic, you integrate from 0 to 2 pi or minus pi to pi is the same. That doesn't matter. It's minus pi to pi and times cosine. It's the same. The formula in 19.2 and 0.3, you can shift the integration limit to fit your problem. As long as the period is 2 pi, it's the same. But this works for periodic function, so it doesn't matter. Yeah, the period is 2 pi, from minus pi to pi is 2 pi. And the formula is given also by 2 pi, is 0 to 2 pi. Right? The textbook equations are 0 to 2 pi, but that doesn't matter. These are all periodic function with period 2 pi. So the integration doesn't matter. Yeah, because you set the function like delta x. So basically, your function has a peak at 0, x and minus pi to pi. And if you say you make it periodic, say, then you have another delta function at 2 pi. That makes it slightly more ambiguous. You integrate from 0 to 2 pi because you hit half of the delta function here and half the delta function here. So you need to make a additional argument that you get half of the value here, half of the value from here. You still get the same result. Okay, it's still possible to do it from 0 to 2 pi, but it's just slightly more inconvenient than if you shift the integration period from minus pi to pi, you just pick up one value. Okay. Instead of having the delta function, the argument is still exactly on the limit, that gives you some ambiguity, but that's fine. You can redefine it. Okay. Is that okay? So the limit in here and the formula change doesn't matter. Okay. Because it's a periodic function, you're expanding it. Although you're saying that you're expanding it over just a finite period, but because you're using the series, you're implicitly assuming that you're treating it like a periodic function. So you copy your function make it periodic first, and then you can use the Fourier series. But finally, your only concern is over this domain. You actually don't worry about outside. But using Fourier series just means that you are by argument you just repeating your function to make it artificially periodic. Then you can use the Fourier series. Is that okay? So because Fourier series is explicitly periodic. Okay, so you can this function, if you evaluate for all x, it will be a periodic function. Okay, but we are doing function expansion, so the main concern is just over the domain you want to do your expansion. Okay, it's a little bit confusing, but once you get the concept, it doesn't matter. No, I mean we already divide the formula. You can use arbitrary domain, the 0 to L or minus L to L. You could redefine your variable such that the same formula, you can divide the formula for whatever the domain you use. That we did that in class. Okay. Okay. You make it 2 pi just for this form. Just write down a formula that is easy to recognize. There's no trick to that. You can always redefine your limit or your variable. Okay. Is that enough for this question? And the part B, in what region is this? Part A is the significance can attach to the constant term. Constant term is 1 over 2 pi. And right, well, you can say this is just the average of the function over the period. Because the period is 2 pi, the average over, the integrate over a delta function always give you 1. So the average is 1 over 2 pi. So the constant term has the meaning of the average over this period, the average of the function over this period. Okay, then part B, what region is this representation valid? Obviously, if you just have one delta function, this expansion is over this domain, so you recover the delta function. And if you extend it, then just like what I said, if you extend this expansion over this period, you get another delta function here, another delta function over here. It's just artificially make it periodic. You have infinitely many delta functions. You extend it to all the real x. Okay, which is if the original function just have one delta x, obviously you cannot go beyond the original domain. If you do that, you have artificial artificial values outside of the domain. Okay, and I think that is what the question is about. Is there enough this A and B part? Okay, okay, good.